Okay, so we're a little out of the dry chapters finally. We're going to move into something a little bit more interesting, thermodynamics. And if you recall, in the first semester, we talked about thermochemistry. And honestly, for the life of me, if it weren't a SUPA course, I'd probably teach the two chapters next to one another. Because to me, when you're talking about thermochemistry, you should also talk about thermodynamics. So we're going to be reviewing some of the stuff or recalling some of the stuff that we learned in thermochemistry and then adding some new things to it. So to begin with, if you recall from chapter 5, energy cannot be created or destroyed. Therefore, the total energy of the universe is a constant. What one system loses, another system, in theory, needs to gain. Energy can, however, be converted from one form to another. So we have chemical energy, we have mechanical energy, we have thermo energy, we have nuclear energy, and it can be transferred from one system to the surroundings or from the surroundings to the system. So this is referring to the first law of thermodynamics, which is the law of conservation of energy. Now we're going to talk about enthalpy and entropy. Enthalpy is the heat absorbed by a system during a constant pressure process. So enthalpy is a form of energy, where entropy is a measure of the randomness in a system. And both play a role in determining whether a process is spontaneous. If you recall from Regents chemistry, systems in nature tend to move toward a higher entropy, meaning more randomness, and lower energy, meaning exothermic. And that should make sense to you. And I'm going to use the same principle I used back then. It's about your room. Okay, when you go home at the end of the day, it's real easy to just drop your backpack on the floor, kick your shoes off, pull your dirty clothes off, leave them in a pile on the floor, and get into something comfortable. Okay, so you just increased the entropy of your room, the randomness, it's now messy, and you used very little energy to do it. On the other hand, if you were to go home, put your backpack on your desk, take your dirty clothes off, put them in the hamper, and take your shoes and put them in the closet or on the boot rack or whatever, that has less entropy, meaning it's more ordered, and you actually had to expel energy to do it. So it's a good way to help remember. So this refers to the second law of thermodynamics. So remember, spontaneous processes proceed without any outside assistance. The processes that are spontaneous in one direction are non-spontaneous in the reverse direction. Do not confuse spontaneous with fast. Spontaneous just means that it happens on its own. The rate at which they happen, okay, are independent of it being spontaneous or non-spontaneous. And don't confuse non-spontaneous with impossible, because I can make a non-spontaneous reaction occur by adding energy to do it. And the prime example of spontaneous versus non-spontaneous processes, of course, would be voltaic versus electrolytic cells. In a voltaic cell, a chemical reaction takes place and energy is produced. In an electrolytic cell, we have to use energy to drive a non-spontaneous reaction to make that energy be produced. And that's kind of unique because the unit that we're doing after this unit is electrochemistry. So what are some things that affect spontaneous reactions? Well, temperature is one for sure, and pressure. Let's look at an example of how these work. So here you can see how temperature affects the spontaneity of ice melting or freezing. If I increase the temperature greater than 0 degrees, what's going to happen? It's going to melt. It's going to happen all by itself. All I had to do is increase the temperature. If I decrease the temperature, it's going to freeze. And whenever we're talking about these types of processes, we have to do it from the terms of system and surroundings. So in this first diagram, you can see that the system is at a higher temperature than the surroundings. And we know that heat travels from high to low. Therefore, a small increment of heat will be transferred from the system to the surroundings. And that would happen until both the system and the surroundings are at equilibrium. In the second diagram, you can see that the surroundings are at a higher temperature than the system, so the system will absorb heat from the surroundings until they're both at equilibrium. So in a reversible process, as you can see here, the system changes so that the system and surroundings can be returned to the original state by simply reversing the process. This actually maximizes the work done by a system on the surroundings. And then there are those that are irreversible. So here you have a piston and you have a movable partition. And then you have a vacuum area and then you have the gas area. If the partition is removed, then the gas spontaneously fills the evacuated space, because we know gases will spread out to fill whatever size container that they are in. When the surroundings do work on the system to move the piston and then compress the gas, here you can see that the gas is pushed together. So the first one is irreversible because there's no work done. The work done by the system equals 0. All we did was remove the partition. In the second example, there is work done on the system by the surroundings. That's increasing the pressure on the piston. So the work done on the system is greater than 0. Irreversible processes cannot be undone by exactly reversing the change to the system, or cannot have the process exactly followed in reverse. Also, any spontaneous process is irreversible. Think about a simple example of magnesium ribbon, okay, that shiny silver stuff in hydrochloric acid. You know what's going to happen, okay? It's a single replacement reaction. It happens by itself. The magnesium displaces the hydrogen, forming hydrogen gas, so you see the bubbling, and then the magnesium combines with the chlorine and the hydrochloric acid to form magnesium chloride, aqueous. We cannot reverse that reaction. I cannot get back my magnesium, and the hydrogen gas escapes. Now, we've talked about entropy before, but we've never given it a variable. Well, this is the chapter where we assign it a variable. It is considered a state function. Recall from the beginning of the year when we first defined state function, it is considered a property whose value does not depend on the path taken to reach that specific value. So, state functions are mass, pressure, density, energy, temperature, entropy, enthalpy. Those are all examples of state functions. And it has the variable S. So the change in entropy, delta S, in a system depends only on the initial and final states of the system, not on the path taken to get from one state to the other. Now, there is a special case of an isothermal process, delta S, which tells us that delta S is equal to the heat that would be transferred if the process were reversible. So that's where you get your QREV, divided by the absolute temperature at which the process occurs. which gives us delta S equals Q ReV divided by T at that constant temperature. So although many possible paths can be taken to get the system from one state to another, only one path is associated with the reversible process. Therefore, we can use that equation that you see right there to calculate delta S for any isothermal process between states, not just the reversible one. So I mentioned this earlier when I talked about entropy and enthalpy, the second law of thermodynamics. The entropy of the universe increases in any spontaneous process. Why? Because entropy is increasing and enthalpy is low. So here you have the entropy of the universe is equal to the entropy of the system plus the entropy of the surroundings, and that's going to equal 0. In an irreversible process, this value would be greater than 0. And this last equation should make sense because any irreversible process is going to result in an increase in entropy of the universe. So before we talk any more about this and how we apply it, we need to look at entropy on a molecular scale. And Ludwig Boltzmann actually developed this conceptual model and gave us a better understanding of entropy and what it looks like at the molecular level. So let's look at the expansion of a gas. You have two molecules, one red and one blue, that start on the same side of a chamber. When you open the valve, what is the likelihood that they remain on one side? Well, you can see when you open the valve, there are 4 possible arrangements. The blue one can stay where it is and the red one can go to the right, or vice versa, or they both can wind up stay on the left, or they both can wind up on the right. So when we examine this a little closer, the probability of the red molecule being in the left flask is 2 and 4. You can see it on the top right, and then you can see it on the bottom left. The probability of the blue molecule being in the left flask is the same, top left and bottom left. Because the probability is 2 out of 4, which equals 1/2, that each molecule is in the left flask, the probability that both are there is 1/2 squared, which equates to 1/4. If we were to apply the same analysis to 3 gas molecules, we would find that the probability that all 3 are in the left flask at the same time is 1/2 to the third, or 1/8. Now, what if we used a mole of gas? 1 mole. You know that 1 mole is 6.02 times 10 to the 23rd, Avogadro's number. The probability that all molecules are in the left flask at the same time is 1/2 raised to the n, or Avogadro's number in this case. This is an extremely, extremely small number. Therefore, it is essentially 0 likelihood that all the gas molecules will be in the left flask at the same time. So by looking at this analysis of the microscopic behavior of the gas molecules, that can then lead us to make some inferences about the expected macroscopic behavior. The gas would spontaneously expand to fill both the left and the right flasks, and it does not spontaneously all go back into the left flask. So we know that this confirms our theory that the tendency of molecules is to spread out among the different arrangements they can take. Before the stopcock is opened, of course, there's only one possible arrangement. All are in the left. But when that stopcock is opened, the arrangement in which all the molecules are in the left flask is but one of an extremely large number of possible arrangements. The most probable arrangement would be those in which there are essentially equal numbers of molecules in both flasks, which is what I'm showing you here, that gases would spontaneously expand to fill the volume given. And here would be when they would have approximately equal molecules on both sides. And they would move back and forth until they reach that equilibrium point. So when we talk about thermodynamics, we're looking at bulk properties of substances. We're looking at the big picture of what's happening to the molecules. We just looked at it at the molecular scale, but how do they relate? Well, we use statistics to relate them, and that is called statistical thermodynamics. We begin so by looking at a microstate, one single possible arrangement of position and kinetic energy of molecules. And the biggest problem that I've seen with this type of thinking is students having some difficulty distinguishing between the state of a system and the microstate associated with that state. The state describes the macroscopic view of the system, for example, by pressure and temperature of a sample of gas. The microstate is a particular arrangement of the atoms or molecules of the system that corresponds to a given state. So how are the particles arranged at that particular pressure and temperature? So to do that, we use the Boltzmann equation, where W represents the number of microstates, okay? Entropy, S, is a measure of how many microstates are associated with a particular macroscopic state, and the connection between the number of microstates and entropy of the system. So you have K, which is a constant, the Boltzmann constant, which is 1.38 times 10 to the negative 23rd joules per Kelvin, and the ln is the natural log. So since entropy is a state function, we need to have the final value minus the initial value to give the overall change. So here, we can rearrange, so we have delta S equals K ln W final minus K ln W initial. We can rearrange that formula to get K ln W final divided by W initial. And entropy will increase with the number of microstates in the system. And to be honest with you, I've never seen them use this formula on a test or ask this. There's quite a few other formulas that we're going to be working with that are much more important, and having the conceptual of understanding of what is an increase in entropy or a decrease in entropy as far as states of matter are concerned, and how temperature and other variables affect entropy. So speaking of other variables, the effect of volume and temperature change on a system. Clearly, you know, if we increase volume, then you have more space. So there's more positions for the molecules. And this obviously will result in more microstates, therefore an increase in entropy. So microstate, that little individual snapshot of where the molecules are at that particular state. Also, if we increase temperature, then we're increasing average kinetic energy, we're increasing collisions, therefore that's going to increase distribution of, that this results in a greater distribution of molecular speeds, and therefore are more possible kinetic energy values, resulting in more microstates, resulting in more entropy. It's that domino effect, and it's pretty intuitive when you think about it from what's happening with the particles. Envision in your mind what's happening with the particles as these changes are taking place. So we have to mention how the molecules are moving. Remember that all molecules are three-dimensional. So even though we're drawing them on paper, you have to be able to envision them in your mind of what's happening. So there's different types of motion. You have translational motion, and that's the movement of the entire molecule from one place to another. For example, in the gas chamber, opening that cock stop and the molecules going from one chamber to another would be translational. It's actually moving position. Vibrational motion is the periodic motion of atoms within the molecule. So the molecules themselves moving, and then or vibrating while they're attached to one another. And then you have the rotational movement about an axis of the molecule. So as it's moving from one place to another, it's also spinning, okay? I'm not saying that it's spinning fast, but it is rotating about an axis or a plane as it moves. And then the molecules themselves are vibrating. So if you put all these together and talking about entropy, randomness on the molecular scale, it should make sense that the number of microstates, those snapshots, and therefore the entropy tend to increase when you increase temperature, increase volume, and increase the number in general of moving molecules. So this is just Regents chemistry. You know that the entropy of gases is greater than the entropy of a solid based on how the particles are arranged. So the entropy of a system will increase for processes where gases form from either solids or liquids, liquids form or solutions form from solids. So going from the solid state to the liquid or the liquid or aqueous state, and also the number of gas molecules increases during a chemical reaction. So I'm just going to quickly review something that you already know. So they have 3 examples of water in 3 different physical states: ice, liquid water, and water vapor. And as you know, particles arrange themselves in a very rigid crystalline structure, very ordered. There's the motion of the particles is vibration only, and this would give us the smallest number of microstates. And then if you go all the way to the gas side, you have the molecules spread out. There's complete freedom. You have translational, vibrational, and rotational movement. This gives us the largest number of microstates. And in the middle, you have water, which is somewhere between, obviously, the solid state and the gas state. Here, you have vibrational and rotational movement the most. You have more microstates than you would in the solid state, but less than what you would have in the gas state. And you have increased freedom with respect to translational movement as compared to the solid state. But obviously your translational movement would be less than what is in the gas state. In the bottom left picture here, you can see how entropy changes when an ionic solid dissolves in water. The ions become more spread out and disordered, but the water molecules that hydrate the ions become less disordered. And then in the last picture you have on the right, you have a chemical reaction. And here we can actually see a decrease in entropy. because you've got 2 moles of nitrogen monoxide and 1 mole of oxygen gas on the left, which are your reactants, and then you're forming 2 moles of nitrogen dioxide. So your overall number of gas molecules decrease, which means that your entropy is going to decrease. So next we're going to talk about the third law of thermodynamics, which we haven't talked about yet. This is a new law. If we decrease the thermal energy of a system by lowering temperature, it should make sense that the energy stored in translational, vibrational, and rotational motion are going to decrease. As less energy is stored, the entropy of the system is going to decrease because it's going to have fewer microstates available. And if we keep lowering the temperature, do we reach a state in which these motions are essentially shut down, a point possibly described by a single microstate? Well, we use the third law of thermodynamics to address this. The entropy of a pure, perfect crystalline substance at absolute zero is going to be 0. So if S equals K ln of W, and there is only 1 microstate, then that means that equals K times the ln of 1, which is going to equal 0. So back in thermochemistry, in the first semester, we had discussed how calorimetry could be used to measure delta H for a chemical reaction. But there's no comparable method for measuring delta S. However, the third law of thermodynamics establishes a 0 point for entropy, and we can then use experimental measurements to determine the absolute value of entropy S. When we do this, the values for elements are not going to be 0 joules per mole Kelvin at 298 because you're increasing temperature. And it should make sense that standard molar enthalpies of gases are going to be greater than that of liquids and solids. The standard entropies are going to increase with molar mass because molecules become more complex. Also, standard entropies increase with the number of atoms in a formula because it leads to more microstates. So table 19.1 is a standard enthalpy table out of the chapter in the book, giving you an example. I want to explain a couple of things. First, I want to say that the remaining standard entropies are located in the appendix at the back of the book. And when you look at S naught, which is what it says right there, that refers to substances in their standard state. And the standard state is defined as the pure substance at 1 atmosphere and 298 Kelvin. So again, you'll find them at the back of the book, I believe in Appendix C. Unlike enthalpies of formation, standard molar entropies of elements at the reference temperatures of 298 and 1 atmosphere are not 0, where for formation, right, delta HF, they are 0. So that's one difference. The standard molar entropies of gases are greater than those of liquids and solids, which should make sense because gases have more entropy. Standard molar entropies generally increase with increasing molar mass. So you can see as you compare H2 to N2 to O2. They're all gases, they're increasing in entropy, and they're also increasing by mass. Standard molar entropies generally increase with an increasing number of atoms in the formula. which you can also see. C6H6, big molecule, greater standard entropy. And these are just some more. And you can see that they tend to decrease for metals by themselves or ionic substances. So entropy changes can be calculated for a reaction very similar to the way that we calculated delta H back in the fall, where your change in entropy is equal to the sum of the entropy of the products minus the sum of the entropy of the reactants, where N and M are the coefficients in the balanced chemical reaction. So remember where we looked at the value up in the back of the book, we multiplied it by the coefficient, and then we did products minus reactants. We're going to do the exact same thing that we did for delta H here for entropy. This slide is kind of repetitive because I already talked about it. Heat that flows into or out of a system changes the entropy of the surroundings. We already talked about an isothermal process where your change in entropy is going to be equal to Q of the surroundings divided by T, which is going to equal the opposite for the system. So it's going to be negative Q of the system divided by T, because what one system gains, another system loses. So the magnitude is exactly the same, the sign changes. At constant pressure, the Q of the system is simply delta H for the system. And I've already talked about this, we're just kind of reviewing. The universe is composed of the system and the surroundings, so therefore the universe, the change in entropy is equal to that of the change in entropy of the system plus the change in entropy of the surroundings. And we know when the change in entropy of the universe is greater than 0, then it is spontaneous. Now, before I go to the next slide, I'm going to tell you that my next slide is different from your next slide. There is no reason for them to go through the equations, so I took the next slide out. It shows you how they arrived at a specific equation for delta G. I am going to put in a different slide that has some different equations that I would like you to write down before we get into some practice. So this next slide I'm going to show you is not in your handout. So I just want to stop for a minute and get our boundaries, because there's a lot going on with thermodynamics. So we have already calculated delta H 4 different ways. We did it using calorimetry, Q equals MC delta T. We did it using Hess's law, where you add the different reactions. So you've got 2 smaller reactions, and then they result in a final reaction, and you either have to have a reaction, reverse a reaction, and then you have to adjust your delta H, I think you recall this, and then sum that up. Then there was Hess's law version 2, where we did sum of the products minus sum of the reactants. That's using delta H. And then there was bond energies, where we take the energy of the bonds broken minus bonds formed. So in Hess's law 1 and 2, it was basically working with the reactions. In bond energies, it was reactants minus products. And now we just talked about delta S, which is calculated the same way as Hess's law 2, sum of the products minus sum of the reactants using the entropies. And I need to specify specifically, because the PowerPoint from the chapter doesn't go into this, that in the back of the book, your delta S is given in units of joules per mole dot Kelvin, and you typically have to convert it to kilojoules per mole. Next, we're going to move into calculating delta G. Okay, I'm going to talk about delta G in a minute, but before we do, there's going to be several ways that we can calculate delta G. Delta G is equal to delta H minus T delta S. That's the most common that we're going to use. You can also calculate delta G by doing sum of the products minus sum of the reactants. Then in the next chapter, it's not chapter 17, you can change that to chapter 20 because it's 20 in this book. On electrochemistry, we're going to calculate delta G using negative NFE, which has to do with Faraday's constant and moles of electrons. And then we can also, lastly, calculate delta G using negative RT ln of K, and you know that K is the equilibrium constant. We've already calculated that. So in this unit, we're going to be using things that we've already used before in our calculations. And this I wanted you to write this down, stop the video and write this down, because this screen is extremely important in keeping you focused into the various ways that we can calculate energy changes and entropy changes. So let's talk about delta G now, Gibbs free energy. If delta G is negative, the forward reaction is spontaneous. And I want to tell you something, this is often difficult for students to understand, because when we talk about delta S being positive, we are talking about entropy, randomness, so a positive delta S is spontaneous, but a negative delta G is spontaneous. If delta G is 0, then the system is at equilibrium. And if delta G is positive, then the reaction is non-spontaneous. But it could be considered spontaneous in the reverse direction. So let's look at the formation of ammonia in the Haber process, as you see on the right-hand side here. You can see that when you have pure nitrogen and hydrogen in greater quantities than NH3, which is the left side, right? You have purely N2 and H2. No NH3 is formed yet. At this point, your Q, right, concentrations would be less than K. So that's going to drive the forward reaction, and NH3 forms spontaneously. However, on the right, if there is more NH3 in the mixture relative to the reactants of N2 and H2, then your Q would be greater than K, and the NH3 would decompose spontaneously into N2 and H2. And in the middle, you have your equilibrium mixture where Q is equal to K and your delta G would be 0. I already talked about this. Delta G, sum of products minus sum of reactants, where N and M are your coefficients. These are some things that are used in establishing standard free energies. So solid, standard state, pure solid, liquid, pure liquid, gas at 1 atmospheric pressure, solution if it's 1 molar. And if it is an element, I2, neon, your delta GF is equal to 0 for an element in its standard state, similar to your delta H, not similar to delta S. This table is extremely important. It helps you understand how signs of delta H and delta S affect spontaneity. And we're looking at it from the standpoint of delta G equals delta H minus T delta S, that formula. So if in the first scenario, if you have an exothermic reaction, so negative delta H, you have an increase in entropy, that means your negative T delta S is going to be negative, which means that your delta G would be negative. So this is spontaneous at all temperatures. In the opposite of that reaction, so they give you the formation of the decomposition of ozone into O2. The opposite of that reaction, clearly then, your delta H would be positive. Your delta S is now negative. You have a decrease in entropy because you went from 3 moles of gas to 2 moles of gas, which means that your negative T delta S is going to be positive, which means that your delta G will be positive, which means that it's going to be non-spontaneous at all temperatures. In the example of a change in state of matter from water liquid to water solid, right there you know your delta H is going to be negative because you're going from liquid to solid. You know that your delta S is going to be negative. You're decreasing in entropy because you're becoming more ordered, forming a crystalline substance. So your negative T delta S will be positive. Now, your delta G could be positive or negative depending on the temperature. It would be spontaneous if it was a low temperature, non-spontaneous at a high temperature. The opposite of that is solid to liquid. So your delta G and delta S are both positive, which means your negative T delta S is negative, which again means that your delta G could be positive or negative depending on the temperature. In this case, it's going to be the opposite. It would be spontaneous at a high temperature and non-spontaneous at a low temperature. It's really important that you understand how to do the headwork on this, because sometimes you'll get theoretical questions and you need to be able to say what would happen. So looking at this more closely, how does delta G change with temperature? Since reactions are spontaneous, meaning if delta G is negative, the sign of the enthalpy and entropy and the magnitude of the temperature matters to spontaneity. Another formula that I listed on that page was delta G equals delta G naught plus RT ln of Q. So under any conditions, standard or non-standard, you can find free energy in this way. However, you have to assume that under standard conditions, concentrations are 1 molar. So Q would be equal to 1, and then the ln of Q would be 0. So that last term would drop out. And we're going to do practice with these in just a second. At equilibrium, Q equals K. You know that. Therefore, delta G would be 0. We just went over that. And the equation becomes 0 equals delta G naught plus RT ln of K. You can then rearrange to solve for delta G naught equal to the negative RT ln of K, and then subsequently rearrange to solve for K in the last formula. So at this point, you have a handout with a couple of problems, then followed by a POGL. So work on that next.